Hi everyone, I'm Yue. I'm excited to present our CVPR 2026 highlight paper, Refracting Reality, Generating Images with Realistic Transparent Objects. Given a text prompt, our method Snell generates both a perspective image and an auxiliary panorama. The final perspective image contains a transparent object with physically correct refractions and reflections. So why is this task challenging? Let's look at an example. At first glance, this glass sphere may look plausible, but if we look closer, the model simply hallucinates arbitrary contents inside the glass sphere, while the background content should be flipped and appear there through refraction. As we can see, our generated transparent sphere closely matches the reference image. We show another example generated by Flux2. The objects in the background should be visible through the glass, but they are completely missing here. Unlike reflections, refractions are tightly constrained by the surrounding scene. In this example generated by GPT-Image2, the mountains in the background do not appear reflected in the lake, while inside the sphere, we can clearly see both the mountains and their reflections, which are inconsistent. These limitations motivate our physics-based generation pipeline, Snell. Starting from the input prompt, we first extract the transparent object, the supporting surface, the object-free prompt, and the panorama prompt. Using the object-free prompt, we first generate a base image without the transparent object, and estimate its scene geometry using Moji2. We then generate a 3D mesh of the transparent object and place it onto the supporting surface detected by SAM3. With the scene geometry and object mesh, we run ray tracing to compute several warping functions between the background, the transparent object, and the panorama view. We first apply the refraction warping to project background content into the transparent object region. Next, at each denoising step, we compute the Euler estimate for the perspective branch, which is the estimated clean image at the current time step. We then decode it into image space and blend with the refraction warped perspective image. We repeat these steps until we get the final image. However, this process cannot capture consistent information about the unobserved region, such as objects that are occluded or out of frame. Therefore, we add a panorama branch, which also gets warped and blended. At each denoising step, a panorama viewed from the object center is generated. It is a 360-degree image capturing what we can see from the center of the transparent object. We warp the panorama to the perspective view and blend it with the two perspective images. At the same time, we also warp the two perspective images into the panorama view and blend with the panorama branch. However, this process does not capture reflections behind the camera. So, we warp the panorama using the reflected rays and blend this with the updated perspective branch using the Snell equations. Finally, both branches are encoded back into latent space and used for the next denoising step. Now let's move on to the results. We first show a Blender reference image rendered using the background and foreground mesh. The black regions correspond to rays that hit missing geometry caused by holes in the depth estimation. Here we show a result generated by GPT-Image2. The glass sphere region is obviously inconsistent with the background. In contrast, our method produces a physically plausible glass sphere. If we switch between our results and the reference, you can see that our result closely matches the reference in the transparent object region. We now show another Blender reference with a more complicated transparent shape. Our result is not only visually appealing, but also physically correct. For more results and details, please read our paper or check our GitHub repo using the QR code on the screen. Thank you.